10 points.
All right, we are starting 10.6 and 10.7. One of them is parametric mode, and one of them is polar mode. One of them is parametric, one of them is polar. I had you guys, for those of you just joining us, sophomores, hope your test went well. But for the rest of you, the juniors are laughing. They should be.
That was us. Sorry, guys.
Meaningless.
It's a very salty morning. Let's go. Very salty.
All right, coming back. So I had the kids. People just joining us. We went to mode. I had them play around with these middle two, par, parametric, and polar. Par, parametric, and polar. I had them play around specifically with polar because he's the funniest one. When you hit y equals, r's show up, and if you hit the variable button, a theta shows up, hence why there's the third comma over a theta in the variable button. I had them try to graph that, and a few problems we had. Number one, we needed to zoom out to see anything. Number two, some people were in radians and saw all kinds of funky things. Number three, some people were having way too tiniest steps. Now, all of those are dilemmas that we're going to talk about specifically in section 10.7. However, just to show you that some of these things are fun, kiddos, what was I actually having you graph? It was supposed to be a spiral. Fun. Anyway, come back.
Wow.
Whoa.
Wow.
Now, if you're like, wait, it's going the wrong direction, I wonder if we could put like a negative or something and have it go a different direction. I wonder if negative changes it. What would that do? Oh, it is going a different direction. Anyway, so I had you guys doing a spiral, right? Now, here's some things that could have gone wrong, and we'll talk about them in more detail in section 10.7. Hold on, it's taking a while. Why is it taking a little bit? Because it's literally going from 0 to 1,080 by sevens. How many sevens are in 1,080? Like hundreds? Well, 100 something. So it had to do 100 different points that it was graphing. So that takes time. For those of you guys that had a 0.1 here and it was taking your calculator forever, yeah, it's because there are tons of 0.1s in 1,000, right? But we can make fun, or we can have some fun with this. What if I was to make it too big of a jump? What if we were to go by 200s? Kiddos, how many 200s are in 1,000, approximately? How many points is it going to graph? 5. Did you see that? It did 1, 2, 3, 4, 5. And it was taught in the programming to connect it. So those of you guys that got funny things, the jumps were too big. What if we were to do something like, we could have more fun, some of you did some crazy things. What if we were taking too big of jumps, but it graphed more? And we can have all sorts of crazy things, right? And that's ultimately what some of you guys were doing. What if we were to do, this will make it more fun. Guys, radians, do they measure angles the same way as degrees? No. How many degrees does it take to do one full rotation?
380.
Degrees, 360 to do one full rotation, the whole like 2 calzones. How many radians does it take? 2 pi, which is approximately what number? 6 something. So radians accomplish in 6 what degrees accomplish in like 360. So if I change radians, but if I still have a degree window, now I'm going to make it back to the normal degree window because this one was a distorted degree window. We'll do like 1,080. Those are a few rotations around the circle. And let's go by like 10s instead of 5s. It should still be fine. This is for degrees, though. This makes sense for degrees. Do a few rotations, like 360, 720. If we went again. Oh, that would be 1080. Oh, that's why I chose that number. Anyway. But this isn't a radian measurement. This is a degree measurement. What happens? What is it doing?
You get Patrick the Star. That looks like the word art that you get when you're playing around in MSP. It's actually pretty good. It looks like
You're
yeah.
Now, wait, pause. Do you guys see what it was doing? It was jumping different places in the rotation. It wasn't smoothly getting the whole rotation. What would be a more proper way of getting this? Because this, okay, long story short, we have to learn how to use our graphing calculator to be able to visualize anything in these two modes, okay? If I'm in radian mode, do these angle measurements make sense? No. If I want a few rotations in radians, how high will I go? 2 pi, 4 pi, 6 pi, 8 pi, something like that, right? Let's do 6 pi, because that was 3 rotations like we did before. But if I'm going to 18, am I going to take jumps of 10 to get there?
No.
Yeah. Imagine that you're driving in a car and you're like going on a trip and you're trying to like map your trip. If we just check where you are like today and then tomorrow and the next day, do we know where you've gone in between? I have no idea. In order to have like an actual full timeline, like say you were like, I don't know, witness of a crime or something, you're trying to retrace your steps and think about what happened in that whole timeline. You're not just going to find like 1 or 2 places. This will only get 1 jump in between 0 to 18. I want lots of jumps. So this is when a point 1 makes sense. I want lots of jumps between 0 and 18, point 1. Let's see if it looks the same as the degree one when it was being graphed properly.
Looks like a dot, right?
Did I not change the radius?
I think your
Hold on.
Y value,
Did I change something? Oh, that's good. Yes. Where
your
did
Y
you-
value, keep it 640.
It's too small this start. It just feels like a dot.
Do you want to use one of our calculators?
If you guys done it already, go to radian mode. Do 0 to 3 pi or 4 pi. And then go by point 1.
I didn't want to create different dots.
Okay, it's going. It's just going smaller. Sorry. I forgot the degrees. This is like the one special case, degrees, since they're big. The theta makes a big graph, whereas radians, since they're small, it makes a little tiny graph. But it does make it spiral if you zoom in. And if we were to go to whatever, would I have like 4 pi, 3 pi, something like that? Would we see a spiral as well? I just changed it wrong. Okay, so the proper picture for r equals theta is always a spiral. But the dilemma is, depending on your mode, depending on your window, there are so many places that can go wrong. So guys, even though we are going to use our calculators, we're going to need to learn how to use our calculators. So I introduced 10-7 because he's kind of more fun to see like funny things in your calculator. You can make these weird like star things, these weird rose things. You can make limaçons, which are little snails. You can make little pesky things that look like distorted hearts. You can make flowers. That one's kind of funny. You guys want to say flower one?
Yes.
But as soon as we finish the flower one, then we're going to go to parametric mode and learn about him. So let's go ahead and do something like sine. This is fun. Let's do 5 theta. Let's do 5 theta. Just do zoom standard. Oh, it's too small because I'm in radian mode.
Sine of what?
5 theta. I'm just going to go from 0 to 2 pi. That should be good. If I'm going to make my flower a little bit bigger, so I need a horizontal, a vertical stretch, or we should just say a dilation. And then make my petal the length of 5. There we go.
I make it like this.
That's a much better font than what I got.
That's cute.
That's fun. But your mode has to be proper, meaning you have to be, if you're in radians, you have to have like a small little range with like point ones. If you're in degrees, in order to get this picture, that would not show you anything. It's way too small. So if you're in degrees, you would have to. I don't know why things are good. In your degrees, a better window would be like 0 to 360, taking bigger steps, like steps of 5.
Oh no.
And then you'd be able to see the exact same thing.
My calculator's gonna be horrible.
Why did I get that curvy?
Can't you? Polar is curvy because it's based on, in a sense, kind of latitudes and longitudes, so everything is circular. It's a whole different thing. Alright, cool kids, let's go ahead. That was fun. That was a good introduction. Let's go find parametric mode. Par. What's different for those of you guys that went into par mode? T's. T's are our variables. And second of all, did you guys notice, did you try to type anything in and then like try to graph it and it wasn't working?
Yeah.
Go. Maybe I didn't do anything like exciting enough. Maybe like, I don't know, t squared plus 1. Okay, go. It's because parametric functions come in pairs.
Oh.
Parametric functions come in pairs. And so in order to graph parametric functions, I need not only x, but I also need y. But if you guys notice, we already looked at this with polar. What's new in parametric? Not just x's and y's, but also t's. So polar and parametric both have an extra variable that we need to define in our window. So we have an extra variable also in our equations. Parametric come in pairs. I define x and y separately. We'll talk more about y in just a second. All right, let's open 10-6. Nice thing is we're just introducing a lot of stuff today.
Wait, so we're on 10-5. So we're skipping 10-5?
Oh, I put 10-5. Sorry, I was skipping 10-5.
Okay.
10-5 takes all the conic sections and says, hey, how do you twist them and not just make them up and down and right and left, but make them in the middle?
So, yeah, let's
You don't want to do that?
okay.
I liked instead the rotating of conic sections as a last section. Because rotations come back in calculus, so I wanted to give you guys some experience in quadric surfaces and three-dimensional revolving of shapes. So we're skipping the rotating of shapes. All right. If we were in function mode, guys, we'd have a normal equation, no big dealio. To get this nice little parabola, we do negative x squared over 72 plus x, right? No stress, no big deal, nothing crazy. And could this model, like the movement of a, I don't know, say a ball or something, a ball that's being thrown or something that's being shot, that could model the movement pretty well, right?
Do you want us to write like all the windows,
No, it's not too stressful. Don't stress too much about it. It's more for the example's sake. My question is, does all of this make sense? Graph an equation, make a window so you can see the proper path of the particle. Yeah? Okay. My question to you is,
Would zoom fit help?
sometimes. Sometimes it helps and sometimes it just kind of doesn't know where to go. And this one probably zoom fit would help, and I think that's actually how I figured out that window. Guys, when you find the maximum, what does that tell you if this was modeling, I don't know, like a ball that was being thrown?
Maximum height of the maximum distance.
Good, maximum height.
Distance.
So that'd be the y value, right? Move my mouse was right on top. The maximum height would be the y value of how high it goes is 18. What's the 35 point mm-hmm.
Is that distance or
96?
time?
What does that stand for?
Is that time or distance?
Y is how high. What does x stand for?
At a certain time. No? Really? Distance?
Y is how high and x is how far. This was the path that a ball was being thrown. Let's say a football pass is being thrown, right? The highest part of its path is 18. And that would be around the, well, if we were measuring that was a 0-yard line, that'd be the 36-inch yard line, right? How far it took to get to that maximum height. Question, what would these little points right here on the x-axis stand for?
Initial and
Why does it have to be initial there? Why can't initial be down here somewhere?
because it doesn't exist.
Why?
Because that would be in a negative field and you can't have a negative field in reality.
Negative height. Don't use field, but use height. If this is the height, if it goes a height of 18 feet or 18 yards or 18 whatevers, if it goes a height of 18, then what does that mean the axis represents? A height of, if this is a height of 18, when y is equal to 18, on the x-axis, what's the height of the thing being thrown?
0.
0. Oh, so if it's 0, doesn't that mean it's on the ground? Oh, so when something hits the ground or something is on the ground, we say the height is 0. So why does it not make sense if this is a football being thrown to even look at any of these parts that are underneath? You can't go underground. That doesn't make sense. But if this was a different example, if something was being shot off the top of a tower, and the ground is in here, this is the height of the tower, could it make sense it would go down?
Yes.
So in physics, everything depends on where you define the different initial or beginning heights to be. what you make on the x-axis. Now, this tells us how far, and this tells us how high. What does this not tell us? When, or how long. And that's why we need parametric. We need parametric because a graph of a path that we can do, we can make a parabola. And we can say y equals x squared and say, hey, it's the path something is on. But without going into parametric mode, we can't talk about time because we only have two variables to work with in function mode. So we can say how high, we can say how far. We can say horizontal distance and vertical distance, but we can't talk about time unless we go into a mode that lets us talk about x and y and t. Let me give you a second to go and get this down. When dealing with functions, we only talk about, we call them rectangular functions or rectangular equations. We only talk about x's and y's. So we only have two variables, but what if there's a situation where we care about the x and we care about the y and we care about the time? Hence the need for parametric. Parametric mode is based on something called the parameter. Hey, wait a minute, parameter. Oh, that's why it's called parametric. There's a third parameter, a third restriction, a third variable. And in parametric mode, x is no longer independent. In parametric mode, x is no longer independent. T is independent. In parametric mode, x is no longer independent, t is independent. And if t is independent, that means both x and y depend on t. And that's why in your graphing calculators, when you guys tried to graph just putting something in it for x, it wasn't enough. You need an x of t and a y of t. So x and y are both dependent on t. T is my of, like f of x. T is my of, so it's x of t and y of t, which is why there were two different equations and why parametric come in pairs. So t is the variable button, and x and y are the dependent. And one of the most common applications, I don't know if I should say that, but I'll go ahead and say it. One of the most common applications of parametric mode is the motion or the path of something in movement. And it's called non-rectilinearly, I suppose we could say, or planar movement. In that you're not just going, let's see, in vectors. Well, I don't want to go too high. We're skipping that chapter of three-dimensional vectors. But long story short, we've talked about a lot motion going just in one line. Going right, going left, going up, going down. In calculus A, B, we only talk about motion going right, left, up, down. We don't talk about motion that's moving in a curve. And the reason being is because it's way more complicated than math that's involved. Parametric equations, equations built on or based on time, to have an x and a y change, to have a horizontal change and a vertical change all at the same time, function mode is not sufficient. Parametric mode is what's necessary. So long story short, each of these show the exact same path. Each of these show the exact same parabola in the exact same place. The difference is this one shows from time equals 0 to time equals 2.12, 132. This one shows from the beginning of the movement to the end of the movement, and nothing else. It shows the when. So not only can I find how high and how far, but I can also find when. Jesse. So not only can I find the how far and the how high, but I can also find the when. So with that goes, you guys should already have that written down.
So the t is not dimensional.
Could you graph, like, you know how to, like...
Ready, set, go!
This is so the t is not third-dimensional.
Huh?
The t is not third-dimensional.
Just two dimensions. For third dimensional, we would need
So
a third variable.
the velocity of x and y are constant.
No, the velocities aren't constant, but something would need to move. We would call this planar motion. So there's rectilinear motion, which is where you're moving on a line, just a straight line. Planar motion is you're still moving horizontally, but you can also move vertically like a curve, but you're not moving to the right or left or to the side. You're just moving in one, we would call one plane. So you're just moving straight. But when you start moving something like diagonally, well, that could still be a plane, just be that plane. When you're moving and then you veer, that's entering another third dimension. Does that make sense? And then the math gets even harder beyond that.
I'm just not getting like what the t is for.
Oh, the t is how long. So I'm going to go ahead and as you guys are writing these notes, I'm going to put that equation that was in my calculator on the screen before. I'm going to go ahead and put that in my calculator to show you the time. Because in function mode, it just graphs the parabola, right? You just make a window a certain size, it'll graph whatever function you put in for as long as you want it to go. Parametric, we cut it down. My distracted ones, remember you chose these seats in order to be productive? Just reminding ourselves.
Do we need to remind them to the results of the path and how to sketch? Or is it okay?
The resulting path?
Yeah.
I would skip one line. Okay. So let me illustrate this real fast. Do you guys see that I have this equation on my calculator, right? Okay, cool. So, and I told you this equation is supposed to show us a parabola, just like the one up above in function mode. Obviously, it's a lot different, and we'll see how these two relate a little bit later. But these show, I've told you, the exact same parabola. So if I say, hey, look at my parabola, let's go zoom standard just to make sure. Oh, nope, we know our window, huh? Okay, let's just try and see what's there. What graphs? What? But it's selected, right? And I have the liney thing. And what graphs? Why? Look at what I did to my window. Have I allowed any time to pass? Oh, so nothing's happening because nothing's happened. Now, what if I allow 1 unit of time? That could be 1 second, 1 minute, 1 hour. It depends on how these equations were formed. But what if I allow 1 second to pass? Is something going to happen? Oh, yeah, something happened, right? But my window is way different than this window. So let me change my window just to make it, let's see, what does it look like, guys? 0 to 18 on the Y's and, let's see, 0 to 72 on the X's. Does that sound about right? Okay. Now, one other thing that we could change is to say, wait, if we're only going the unit of 1, maybe polar mode kind of helped you with this. If we're only going the unit of 1, maybe I want some more baby steps than just 10. That's only 10 steps right now. Maybe 0.01 is a little bit more accurate. Now let's check it out. Oh, okay, so in 1 unit of time, yeah, no, literally though. It's a little bit high. Is my graph off? 24 times square root of 2t, negative 16t squared plus 24. Oh, sorry, that t is not supposed to be in the square root. That's what I did wrong. Yeah, that's tricky. Look at that. Nasty, nasty. Okay, delete t. Oh my goodness, you goofs. Okay, now let's check it out. Okay, so 1 unit of time has passed. Da, 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 da. Here he goes, here he goes, here he goes. Is he going to go all the way? Why not? It's only like a second or an hour or a minute. It just stopped. What's going on? Maybe I ran out of room, but maybe I just need to give it more time. Maybe I just need to give it more time. Those are non-stop today. No more sugar for you. Wait for it. Wait for it. Is it going to graph anymore? It just needed more time. So wait a minute. The window says allow 2 units of time. Okay, is it going to make it all the way down?
Bro, I don't think so.
Oh. I need to give it even more time. Does that make sense, guys, what I'm doing? Time says how much of the graph has happened. If we maybe allow 2.5. And to be honest, I think I have it down here, 2.12, etc., etc., etc. Now, hold on. I'm getting impatient. I'm going to change my window and say, go a little faster, please. That's a little annoying. Let's do like 0.05. Okay, there we go. And so in parametric mode, if I was to go ahead and do second trace, and if I was to go ahead and, it's not going there. There we go. Find the value. And here's a little bit of a struggle. There's no 0, there's no max, there's no min, which is kind of lame. If I was to plug in 2.1213203, it would tell me the x height, the y height, sorry, the x distance, the y height, and then the time at which it appears. So you find some new things. The dilemma in parametric mode is you don't have all those those nice intersections, zeros, maxes, mins. So function mode is super nice for that, for the path itself, but parametric mode is nice for the time. It's showing not just the where, not just the how far horizontally, how high vertically, but how long it takes to get where you want it to go. Now, let's go back to here and what you guys were writing. Because we're just trying to get the foundation for parametric mode and like what it is, how to work with it, algebraically, graphically. And once again, kiddos, remember pre-calculus is pre-rest of math. We're just introducing something that would be applied much later on. Let me get my iPad back. Sorry, I think I'm in your smart notebook. There we go. Okay. So, horizontal, vertical components written as functions of time. That's the verbal-like description of what's going on. So we're going to have x being some function in terms of time, like I already wrote. Y being some function in terms of time as well. The plane curve, I'm going to go ahead and call the path. The path of motion, the path of movement. The graph itself is called a plane curve or a planar curve. Some people say P-L-A-N-A-R, planar curve as well. It's a path of motion, and you can literally see what's going on as far as where this ball is being thrown. And you can talk about x and y both in terms of time, t. Now, how to sketch, we're going to go ahead and say, well, you know how in the olden days in Algebra 1, to make like a sketch of a graph before you knew what, I don't know, right now you guys know what parabolas are roughly, and linear functions, and exponentials, and logarithmic, kind of, sort of, and trigonometric. What else? You know, absolute value functions and cubic functions. Maybe you could work with a quartic function. What else do you know? Parabolas. In Algebra 1, it was like, I don't know who any of these people are. Let's just, or I should say graphs. Let's plug and chug stuff. And you would plug in x and get out y, but now we're going to plug in t and get out x and y, right? Now we're going to plug in t and get out x and y. And almost always, we start at time 0. How come? Why don't you start when time is 0? At the beginning. Yeah, just think at the beginning. So we're starting at 0 because that would be, and we're going to say the snazzy physics term for it, that's the initial. That will find the initial position. So when t equals 0 at the beginning, that would be the initial position. And then we might be able to plug in t is 1 and 2 and 3, or t is 5 and 10 and 15, or t is 20 and 40 and 60. Depends on, I don't know, how much time is passing in the model that you're working with. And then you plot the points that you get up above, Now careful, the points that I'm talking about are the x and y points, right? T just tells us when, x and y tells us where. Plot the points, plot the x's and y's in order of increasing values of t, so showing as time is passing, and find the orientation. The orientation is what direction? The orientation is what direction the movement is going in, and that direction is shown by arrows. Arrows drawn in the graph itself. Orientation just says, okay, not only do I see where it's going, and I can find when it's going to be at each of these different positions, I can also see what direction it's headed, and that's what you guys saw on the page before on this one. Do you guys see the little arrows that were drawn? Now this wasn't from the graphing calculator, this is what you would put in after the fact. This tells me the ball is flying how? From here, this direction over here, right? But if the equation was a little different, couldn't we show the ball going this way as well? So we need those little arrows so that we know what direction the object is moving on the path. So that's just called orientation. Put little arrows in. And guys, your graphing calculator does that because it shows from beginning to end. It graphs from the smaller t to the bigger t. So the direction it graphs is the direction that we show with our little arrows. So what if I was to give you something like this? That was actually really nice on this one because what do you guys see over to the right? Oh, I didn't make you plug in. That's kind of nice. I did it for you. Well, sort of. I had the book do it for you. But could you have found this table on your own? I think so. But why didn't they start at 0? They were given a range for the time. Or maybe we should say domain. This gets tricky now. They were given an interval for the time as to when to start and when to end. Now, could you have plugged in something like negative 2.5? Would that make sense in this case? Would something be going on at negative 2.5 if it's going on at negative 2 and negative 1? Ah, sorry. How about negative 1.5? Okay. Time moves continuously. So unlike sequences where we had n was equal to 1 and 2 and 3 and decimals and fractions were not allowed. Time, if something is flying through the air and we map it at negative 2 and at negative 1, we could have figured out what's going on at negative 1.5 in between because it was still in the air, it was still moving. So fractions and decimals are definitely cool. This definitely is a continuous function. My question to you is, how do you take that table and how do you figure out and properly sketch the curve? What would you guys say? Take the x's and y's, yeah, and do what with them? Plug them in. Now I notice my y's are not very big, right? So I'm going to go by 1/2. Is that cool? So I'm going to go by 1/2. I'll make that 1. I'll make this negative 1. And I'll just go by 1's down here. So that's 2, that's 4. Negative 2, negative 4. Okay. So what are we graphing? 0, negative 1, right? Negative 3, negative 1/2. Negative 4, 0. Wait a minute. Negative 3, 1/2. Are planar curves necessarily functions? I need to connect these points. Here's something else parametric lets me do. In function mode, we could never graph a non-function in one equation. It's impossible. Function mode, by definition, only graphs functions, hence why we have to do like plus or minus square roots separately. But in parametric mode, we can graph non-functions. That's helpful, right? Because objects don't just go in functions, they like go in circles, etc. Now wait, pause. This graph is almost perfect. What do I need to add? Pause. Got it. Good job, kiddos, playing with your calculators today. Make sure to bring calculators tomorrow. Pass the word if you see any of the sophomores today. We will finish parametric tomorrow. Bye, guys.